Good afternoon and welcome to MAE 106. This is Discrete Mathematics with Probability. My name is Richard Kohar and this is lecture 31. And in today's lecture we're going to do worked examples of probability distribution questions. Hello Mario. It's good to see everyone here and hopefully you can hear me. Good afternoon. Okay. Good afternoon. It's good to see people in the chat. So today's double period is going to be about probability distribution questions, and we'll work through some examples. Before I go through, there's two things I need to cover. There's another formula for variance. Which can be helpful sometimes. It makes it a little bit quicker. Somebody's asking if we have lecture material on the 7th of December or if we won't have class. I would assume that if there is a lecture scheduled, we will probably be using it either to do material or to do review or to do an old exam. So I will use whatever time they give me to try to give as much help for the exam. I hope that answers the question. So there's another formula for variance that we'll go through. And we also have to talk about then the standard deviation. So going through that variance formula, again, remember it's the variance of a random variable x is the spread or how much on average it is from the expected value. Now, if you're interested to see that if this is why this is true, the proof of this is on page 411. So the interesting part about this one is that we have to calculate the expected value of x squared. It's different than the expected value squared. I know it sounds pedantic, but there is a semantic difference between these two. Because over here, what the expected value of x squared means, that's the summation of all the values of x, where not just the value of x, but it's x squared times its probability. Okay, so what we'll do is we'll go through the example that we had with throwing a die. So here's the example. So let x be the value of a die throw. So what that means is that if I write this out as, let's say if I do it like this, I do x and I have 1, 2, 3, 4, 5, and 6. Now we're going to assume that this is a fair die. And when we say that that's a fair die, it means that all outcomes are equal. So there's 6 outcomes. If they're all equally likely, that means that it should be a 1 in 6 chance. Or sorry, 1/6 of a chance for each of these. And if we do calculate, if I write out, so let's multiply the value times the probability. So that's 1 times 1/6, so that's 1/6. I have 2 times 1/6, that's 2/6. 3 times 1/6 is 3/6. 4 times, so it's 4/6. 5 times 1/6 is 5/6. And 6 times 1/6 is 6/6. Okay, and if I add these all up, that gives me 21/6. And that is the expected value of x. Now, if I want to calculate the x squared part here, what I can do here is do x squared times the probability. So what I get then is 1 squared times 1/6. So what is 1/6. So I'll put that here. I'll just kind of write over here that this was 1 squared times 1/6, which was the probability. Then I would have 2 squared, so that's 4. 4 times 2 . 4 times 2 is 4. Oh, sorry, sorry. So 2 squared is 4. Times that by 1/6, which gives you 4/6. So again, I'll just kind of put this over here. So that is 2 squared times 1/6. Same thing, I can have 3 squared, so that's 9 times 1/6 gives me 9/6. 4 squared over gives me 16/6. 25/6, and lastly 36/6. And if I add those up, 1 plus 4 plus 9 plus 16 plus 25 plus 36 gives me 91/6. And so what that gives me is the expected value of x squared. so I have these two values. And this is the formula that we need. Okay. So again, I have my values. So the variance is the expected value of x squared, so that's 91 over 6 minus the square of the expected value. And if we work this out, well, 21 over 6, that can be reduced down to 7 over 2 squared. Which leaves me 49 over 4. And what we can do is we can write those over 12. So in this case, I'm multiplying this by 2, this by 2. And over here, I would be multiplying it by 3. So just as a quick, so I would have 91 in, so this would be 182, and then I have 49 times 3. 9 times 3 is 27. I have 4 times 3 is 12, plus the 2 gives me 14, so that's 147. So I get 182 minus 147. I believe that's 5. Hopefully. And then 3, and so we're left with 35 over 12. And that works out to be approximately 2.92. Good day. Good to see everyone there. Okay, so everyone was able to see that I was doing arithmetic. So that's what we can actually say then. So if we let x be the throw of a fair die, then the variance of a single die throw is 35 over 12. Now, if we would like to know the distance between the random variable x and the expected value of x, then we can take the square root of the variance, and this is called the standard deviation. So let me just grab a piece of paper. Here's number 2. So here's the standard deviation. So all that is you can think of it as it's just the square root of the variance. Okay. And so that is a measure of the distance from X to the expected value on average. So if we go back, oh, maybe I'll put a box. This is important. So if we go back to our example of a fair die throw, and we had that the variance of a single die throw is 35/12, the standard deviation is just the square root of 35/12. And that's approximately 1.71. Now that's just a calculator. You don't have to do that on the test. It's just the square root. So something like that, that's a nice easy point on a test or the final exam. Okay, so this gives us a little opportunity then to just kind of go over what we have done in the past couple of lectures. So just as a summary, we had that a random variable assigns a numerical value to the outcome from the sample space. We know that we have a probability distribution. All of them must sum up to give you 1. We talked about things such as continuous versus discrete random variables. Continuous meaning like they're real valued, whereas discrete are, so let me just put over here, this is kind of like, these are real valued, and over here, discrete means things that are like natural valued, whole numbers, the integers, the rationals. We had the expected value of a random variable x is the sum of the value times the probability. We talked about things that, such as when we're gambling or games of chance, we consider a game as fair if the expected value is 0. We talked about the variance or the spread from the expected value for a random variable. And so there's kind of the 3 ways that we could express it. We can do it as the expected value or distance squared from x to the expected value. There's just us rewriting the expected value as a summation. Or we could do the expected value of x squared minus the square of the expected value. And lastly, if we take the standard deviation, that's just taking the square root of the variance. So let's talk just a little bit more then. Let's go through some examples. And so like I said before, we have discrete. These are random variables that are discrete or continuous, these mean that they take on discrete or continuous values. So like I said before, discrete means that you can have natural numbers, so that's like 1, 2, 3, 4, dot, dot, dot. That can also mean, let's number this page 4. You can have whole values, which means that it's 0, 1, 2, all the way up. I can have integers, so that includes the negative values. So like 2, 1, 0, 1, 2, all the way up. And it also includes the rational numbers, so numbers that are fractions. Now continuous, those are real values. And the reals consist of the rationals and the irrationals. Okay, so classify each of the following random variables as discrete or continuous. So for A, it says the number of questions that are assigned for a homework. Just in the chat, what does everyone think that this is? Do you think that this is discrete or continuous? Discrete, yes. Yes, it is discrete. Yes, it is discrete, and I know it's likely either the natural numbers or whole numbers. So for instance, you could have, 3 questions assigned. Somebody could say, oh, you could have 0 questions assigned. So that's what I'm going to say with the whole numbers as well. It's very unlikely for somebody to take away questions. So, all right, how about this? The length of time you take to do your homework. What do people think in the chat? Well, that wasn't really the option of crying, but continuous. Continuous, people are saying continuous. Yes, I would say it's continuous. Some people are saying discrete. For those that are saying discrete, why do you think it's discrete? I mean, continuous. Well, for instance, let's say that you have, just to kind of explain why I think that this is continuous, is, for example, you could be on the interval 0 to 1, say 1 hour. And you could be anywhere inside of that hour. So you could be like 0.3 of an hour, 0.5, root 2, it could be anything. So again, it could take on any of those values and not necessarily even a value that could be expressed easily as a rational. Okay, let's move on to C, the number of reams of paper ordered for a university department. So again, reams of paper, meaning those are those big packages of 500 sheets. Yes. I think it's discrete as well. So you're unlikely to order, not only do I think it's discrete, I think it's a natural number or a whole number. You're unlikely to order part of a ream. It's just suppliers don't allow for that. The number of eggs laid each year by a chicken. What do people think for number of eggs laid? Yes, it's also discrete. It's likely to be a natural number. Unlikely to have part of an egg. Number of accidents per year on a stretch of highway. What do some people think? Discrete? Yes, I think it's discrete as well. I think it's probably a natural or a whole number. You can have 0 accidents. And again, it's unlikely to have part of an accident. There's some sort of threshold, something where maybe perhaps the police are involved or there was an accident insurance claim filed. But those would be, you wouldn't have like a half a claim or a half a incident. So there's the reasoning for that. And what about the last one? Length of time to play a game of chess. Continuous, yeah. Good. And again, that's probably the reals. Now, I'll add one more. I know that this is... Let's go E, F, G. Let's go with... we'll call it R. We'll say the rate of accidents. Per week on a stretch of highway. Yes, I would say that this is continuous as well. Good. Are there keywords to look for determining if it is discrete or continuous? I would say certain words like length or rate would lead you more to say that it's a continuous. You can also see here length. I would say when you see things like number, I would say something along the lines of like continuous. Means you usually have to measure. So again, like you could have like using a ruler, you could be measuring what the length of a pen is. You know, that I would say is like a continuous random variable, what the length of my pens are. You know, you sit there and you measure something, or you're timing something, or you're looking at, you know, the length of time. So again, that's a form of measure. Whereas discrete usually means you're counting something. So again, I'm not measuring something. I'm just, how many pens do I have? You know, here's, I don't go and pull out a ruler in this case to measure something. In this case, I'm counting. I have 1, 2, 3, 4, 5, 6. So there's kind of that a generalization that you may be looking for. Your number of no, I do have a finite number of pens. That is for sure. I definitely have a limited supply, even though it may be quite large. Okay. You know, this would be also another kind of one, would be how much ink is remaining in this inkwell. If we measure, say, things in like milliliters, again, I would be measuring or weighing or how much fluid or liquid is left in the jar. It's not something I could easily count one by one. So I'm going to switch to a different pen for this. This one is from the book, and not only that, it's also from the homework, I think. This one says, find the probability distribution for the total number of tails obtained in 4 tosses of a fair coin. So there's a couple of like little keywords. So we got the number of tails. Well, first of all, is this a continuous or a discrete random variable? So if I say let x be the number of tails, obtained in 4 tosses of a fair coin. Yes. That is something that we can say for sure. X is discrete. Let's also, what are the values that x could take on? maybe I won't put that as a... What are the possible values of x? Just in the chat, what do you think? Yeah, we could have 0, we could have 1, we could have 2, 3, or 4. Good. So this says find the probability distribution. So again, we'll have a table we have to do. So some sort of table. If you wanted to, you could maybe do a graph, but that says to find it for the total number of tails. Okay, so what I'll do, oops, try not to go too far off. So we have, let's use, a probability tree. So here's the probability tree. So again, we can have either heads or we can have tails. So again, when we're flipping kind of that fair coin, we can have a head or a tail. So that's the first toss. Gotta make sure that I can have heads or tails on the second. Same thing down here. We can have, again, heads or tails on the third toss. And lastly, we can get one more toss in here. We have the fourth. Heads or tails. Heads or tails. Squeezing that in. Okay, heads, tails. Okay, so there's the probability tree without the probabilities. Okay, so let's start writing in some values. So you get 0.5 probability that you get heads on the first, or you get 0.5 probability for tails on the first toss. What this means here then is, if I granted I have heads, what's the probability that I get heads on the second toss? Well, these tosses are independent. So we'll say 0.5 and 0.5. So 4 tosses. We could also add in here 4 independent tosses, if you'd like. And same thing for this one. And on the third toss, if I had heads, it still doesn't affect the probability that I get on the next one. you can just fill those in. They're all a half. A little bit laborious, but here we go. Just to illustrate this. So these are all a half, meaning that, okay, so I can write out my sample space. I can have 4 heads. I can have heads, tails. I can have heads, tails, heads. Same thing. Make sure that I'm lining this up. Okay, so for this one I have H, T, T, H, H, T, T, T. This one I have T, H, H, H. There we go. So there's my sample space. Here's a question. Is S a uniform sample space? And the answer is we should look at what the probability for each of those each of these outcomes. So over here it's 0.5, 0.5, 0.5, 0.5, or 1, 2, 3, 4, 2 to the 4, so that's 2, 4, 8, 16. So there should be 16. One in 16, 1 in 16. Again, all these probabilities are the same because I haven't changed any of those probabilities. They're all a half. All the way down to the bottom. There we go. And again, so there should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 outcomes. So that's good. So is S a uniform sample space? What do you think in the chat? Is S a uniform sample space? I have 1 yes. I have 2 yes. Anyone else? 3 yeses. 4 yes. Okay. Do I have more people? Yes. Yes, it is. Every outcome has the same probability of occurring. Excellent. So I'll just kind of put that over here, kind of tying everything that we've learned together as we're working through this question. So what we're going to do now is we're going to now try to come up with a probability distribution for the number of tails. And again, x has to be the number of tails obtained in 4 tosses. So here are all the possibilities. Here's the probabilities. Over here, I'm going to write x. So x is going to be the number of tails obtained in 4 tosses. So in this case, or this outcome here, I have 4 heads. So that means that there's 0 tails. There's 1 tail here. And so I'll just work through this list, counting how many tails that I have in each outcome. Over here I have 2. I didn't draw my lines very well. I'll just divide this with another. There we go. So over here there's 3. Over here there's 1, 2, 2, 3, 2, 2. Oops, that's 3, 3, and lastly 4. So I'll draw out just my probability distribution table. So I'll do x. We have our values which we know they're going to take on from 0 to 4. So I'll write out, here we go, 0, 1, 2, 3, 4. I'll just draw another line. Here's the probability that x equals that little value. So there is, what I would do is I would either, maybe I'll use a red pen. So I will count off how many, because I have each of these probabilities are all the same for each of these. So there's only one time where I have 0 for x. So I'll say that here is 0. And so that one outcome is 1/6, or 1 in 16th. Ooh, that's not a very good pen. Okay. Now the next one I'll go is look at 1. So I have 1, 2, 3, 4. And so 4 times 1/16 is 4/16. Now I'll move on to 2. So I have 1, 2, 3, 4, 5, 6. So I have 6 in 16ths. I'll move on to 3. Scanning down my list, I have 1, 2, 3, 4. And lastly, I have just one occurrence where all 4 coin tosses are tails, so there's only 1 in 16th. So there is the probability distribution for the total number of tails obtained in 4 independent tosses of a fair coin. Let's grab a second piece of paper. Okay, so now I have an extension. So like the original question just said, find the probability distribution for the number of tails. But you could also find, because now we have the probability distribution, you can be asked to find the expected value, the variance, or the standard deviation. So if you want to do the expected value, remember we had the expected value is equal to the sum of all the possible values. So it's the value times the probability of that occurring, and then we just add them all up. So I'm just going to rewrite this table again down here. So I have x 0, 1, 2, 3, 4. There's one more thing I should add. As a check, that the sum of all of these should give add up to 1. So I should have that the sum of the probabilities in the distribution should equal 1. So again, I have 1 plus 4, that's 5. 4 plus 1 is 5, so I have 5 and 5, that's 10. Plus 6 gives me 16. So that's 16 over 16, or that's equal to 1. So yes, it is a probability distribution. So just as a small check, that the probabilities sum up to 1. Right? Just to go back, that all probability distributions must sum up to 1. Okay. So here's the expected value, and we need to multiply the probabilities by the value. So I'll write down a second, here's a second row. So I would have 0 times 1/16, or that would be 0 over 16. I would have 1 times 4/16, so that's just 4 times 16. I have 2 times 6, gives me 12/16. I have 4 times 3 gives me 12/16. I have 1 times 4, so that's 4/16. So if I just have my summation over here, we know that those sum up to give me 1. Over here, I have 12 and 12, that's 24. 24, and then I have 4 and 4 gives me 8. So 24 and 8 gives you what? Good. 32 over 16 equals what? Good. Excellent. So we can say that, therefore, we expect 2 tails in 4 tosses of a fair coin. Okay. So we can also do the variance. In this case, we'll say that it's the variance. We'll use that new formula that we used or learned about. So we'll do the expectation of x squared minus the square of the expected value. So what I'll do is I'll just copy down this table again. So over here, in this case, I have to do the sum of all the possible values of x, such that x squared, so x squared the value, times its associated probability. And over here, that's x times the probability. And then you have to do all squared. Okay. Okay, so now I have this table. I need to do the x value squared times the probability. So that's 0 times 1/16, so that's still 0/16. So I'll just put down here, just to explain what I'm doing. That's 0 squared times the probability, 1/16. Here I have to do 1 squared times the probability, so that's 4/16. Over here I have 2 squared, so that will be 4. 4 times 12 is 48. Oh, I gotta be careful because not 48. excuse me. So that's 4 times 6 over 16. So that's 24 over 16. Over here, that would be, maybe I'll write it in pink first. That'll be 3 squared times 12, 16, sorry, not 12, but 4. I'm looking at the wrong row. And then I'll switch over here. 4 squared times 1/16. So that gives me 1. And if I add up 4 plus 24 plus 36 plus 16, what does that get me? In the chat? Yep. 80 over 16. And then 80 divided by 16, that gives me 5. Okay, good. So these are quite nice numbers. While this might have been a little ugly, we have 1, 2, and 5. So let's look at the variance. Again, I'll write out, it's the expected value of x squared minus the square of the expected. So over here we know, we've calculated, this is the expected value for x squared. So again, that's what I've done. It's x squared, so x squared times its associated probability gives me 0 over 16. And I've done it for every single one of them. We add them all together and we get 5. Okay, so we get 5 minus, and then we do the expected value squared. So it's got to be, this is my expected value here. So that's 2 squared. So it's 5 minus 4 gives me 1. And we can do then the standard deviation. It's just by taking the square root of the variance. So the standard deviation is equal to the square root of 1. And the square root of 1 is, what's that in the chat? It's 1. So we're done that question. But as you could see, we did a lot of concepts within that single, well, of course we extended it, but within here, we tested the idea of what a random variable was. I was able to ask you if it was discrete or continuous. We were able to ask, was the outcomes that we've done here for this sample space, is that a uniform sample space? And because the probabilities were all the same, yes, it is a uniform sample space. And from there, what we did was we constructed a table where we assigned the values of x for each particular outcome. So that's what we did. We went through, and from there we constructed the probability distribution. We were able to check that this was a probability distribution because it all summed up to 1. We were able to calculate the expected value of this random variable, which turned out to be 2. So we expected 2 tails in 4 tosses of a fair coin. We were able to calculate the variance, which was 1. And we were able to calculate the standard deviation of it, which also was 1. Okay, let's do a different one. So we've done, this is page 6. Here's a different question. Might be a little bit quicker to answer. So the probability distribution for a random variable x is given as this graph below. And they ask us, calculate x equals 2. So just in the chat, what is the probability that x equals 2? Yes, it's 1/4. Yep. I'll put down 1/4, or sorry, 0.25, because that's what it says for the graph. But yes, also 1/4. What about the probability that x is greater than or equal to 3? Somebody says 0.5. 0.5. I think that sounds good. What I'll do is I'll write this out just to check. So I have the probability of x greater than or equal to 3. X greater than or equal to 3. So that would mean that the probability of x equals 3 plus the probability that x equals 4 plus the probability that x equals 5. So if I add those up, that's 0.25 plus 0.15 plus 0.1. So I have 0.15 plus 0.1. That gives me 0.25. So 2.25 cents. That's 50 cents. So 0.5. How about the probability that x is odd? What do you think in the chat? Oops, I keep. .5 again, half. Maybe I'll write it over, just a second, I'll move C so it's up a little higher so I can see the, so I'll write it over here, C, the probability x is odd. So again, I would sum up where x is equal to 1 plus the probability that x equals 3 plus the probability that x is equal to 5. So I get 0.15 plus 0.25 plus 0.1. So again, same idea. 0.15 plus 0.1 gives you 0.25 plus 0.25 gives you 0.5. Okay. And the probability that x is between 1 and 4 inclusive. So you would just sum up the probabilities at 1, 2, 3, and 4. So that's 0.15, 0.25 plus 0.25 plus 0.15. So I got 50 cents there, and another quarter gives me 75 cents. $0.75, that's 3/4. Okay. Did I do something incorrectly? Maybe I did. Yes, I did. So over here I had the 50, oops. $15 and 15 gives me 0.3 plus 0.5. There's the 0.8. Perfect. Okay, so let's do one more question. Let's try this one. That's 7. Let's do page 8. So this is exercise 9.3.4. It says in the city of Kingston, 21% of the population have unlisted phone numbers. So 21% have unlisted phone numbers, and none of the residences have more than one phone number. A mathematician rides into a town and selects 2,100 names at random from the phone book. How many of the selected phone numbers would the mathematician expect to be unlisted phone numbers? Expect unlisted phone numbers. For someone that said 0 in the chat, why? Why is it 0? Exactly. They're not in the phone book. And why am I showing this exercise is because oftentimes people get into such a algorithmic or just a robotic approach to it, to doing problem solving, that they're just looking for numbers. Same thing as I've been doing, which is highlighting and selecting certain words that I see and go, oh, I see 21% of the population, and I see 2,100 names. So I have kind of like, what I want to do then is I would just take those two. I have 2,100 people times 0.1, and so some people would say they'd expect to see 441 names to be unlisted. But that's not the case. Because we have to read this very carefully. While we have kind of this population of Kingston. Here's Kingston. And we have these people here. Let's say that these ones are unlisted. The mathematician is not picking from that set. Excellent. Okay. Let's do this one. So we have, if a random variable x is the number of 6s that appear when an ordinary die is thrown 4 times, what is the probability that x equals 2, is less than 2, less than or equal to 2, greater than or equal to 2, greater than or 2, and that x is between 1 and 4. So what I would do is, let's do a probability tree again. I'll just answer this question as is. We have 4 times. Okay, so I'm going to do either you get a 6 or you don't get a 6. So I'm going to say oops, you rolled a 6 and you did not roll a 6. So there's the first throw. You'd think I'd have learned by now to space this out a little better. Let's do this a little bit bigger. Got more space. So you can have it or not. So there's the first. This is being thrown 4 times. Here's a 3rd time. So I have 2 outcomes for each throw, so it means I'm going to have 16 outcomes. So here's the first, the second, the third, and here's the 4th. So again, so here's my sample space I can do. I can do check, 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 check. Check, 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 nope. I'm just working through the list. So there's my sample space. And what I should do is I should also label my probability tree. So over here, I have 1 in 6, right? So the probability that I roll a 6 on the first row, that's 1 in 6. And over here, it's the complement, so I got 5, 6. Same thing over here, I would have, the dice throws are independent, so I would expect that given that I rolled a 6 on the first one, I would still have a 1 in 6 chance of rolling a 6 on the second roll. And the same thing for the third and the fourth. And the complement also would stay the same. I'm just taking my, there we go. So there is the tree. And over here, started to run a bit out of room. So I can actually go through here and count if, since x is the number of 6s that appear when an ordinary die is thrown 4 times. So over here, this would be 4 6s appear, 3, 3, 2, 3, 2, 2, 1, 3, 2, 2, 1, 2, 2, 1, and lastly 0. So let's just extend this over here. I'm running out of room. Move some space over here. There we go. And we can calculate the probability then for each of those outcomes. So over here you have 1 6, 1 6, 1 6, 1 6, so that's 1 6 to the 4th. So that's 1 6 to the 4th. And what's that equal to? Just in the chat. 6 to the 4th is what? It's 1, 2. Oh, did I make a mistake? You have XX check twice. Oh, okay. Let's make sure that I go through. 1.5. Okay. So again, check. So it's XX check twice. Oh, I see it. Yes. Yep. Thank you. So we have 1 over 6 to the 4th. So that's, somebody has said it's 1296. I'll believe you. Over here, now I have 1 to the 6 cubed times 5 over 6. Over here, I'm going to go to the third one. So that would be 1 and 6 cubed. And then I have 1, 5 over 6. For the 2, I have 1, 6. That happens twice. And I have 5, 6 happening twice. For the 3, I have 1, 6, 1, 6, 1, 6, so 1, 6 cubed over the 5, 6. And is anyone noticing a pattern yet? Look at this. With the 3s, like where I have 3 6s up here, it's 1 6 to the 3rd times 5 6. And the same thing happens again here. 1 6 cubed, 5 6. Same thing over here. I have 1 6 cubed times 5 6. The 2s, I wonder if it'll be the same. So let's have a look. So I have 1 6, and that happens once and twice, so 2. And then I have 5 6 and 5 6. That's squared. Same thing happens again. 1 6 and 1 6. If I have 1, I just have 1 1 6. And the remaining cubed. So I have 1 2 3 1 6s times 5 6. Same thing for 2, so that'd be 6 squared, 5 6 squared, 1 6 squared, 5 6 squared. I have 1 6, so in this case there's only one of them, and 3 5 6s. And lastly, I have, I'll put 0 here because there's none of them. So 1 6 to the 0, that's still 1, and 5 6 to the 4th. And that's how I'm going to write out the probability distribution. So I have all those. So I'm just kind of running out of room here, but I have the probability distribution. I have this happen. So there's x, so there's 0, 1, 2, 3, and 4. So the probabilities here I have for 0 was 1/6 to the 0 times 5/6 to the 4. For 1, I had the probabilities here. I had 1/6 times 5/6 to the 3. I had 1/6 to the squared, 5/6 squared, 1/6 cubed, 5/6, and lastly 1/6 to the 4th, 5/6 to the 0. Now, what I have to also do, though, is I have to count how many times these have occurred. So, for instance, with 0, this only happens once. So I'll just multiply that by 1. So those are the probabilities. For 1, this happens 1, 2, 3, 4 times. So I'll write down 4. For 2, this happens 1, 2, 3, 4, 5, 6. So that happens 6 times. And lastly, for oh, well, I have one more, but there's 3. 1, 2, 3, 4. And lastly, I have just 1 where it occurs once. So there is the probability distribution for this. And notice that I didn't have to do any extreme calculations here. I can just leave it like this. So I've come up with the probability distribution. Here's a question, though, I should ask. Is this sample space uniform? Is the sample space uniform? That's right, no. I'm going to say no, and the reason for that is because if I go back to here's all the probabilities that I've listed. Here's the probability of 1/6 to the 4th. That's 1/1296. And here, this is 1 cubed, so that's 1 times 5, so that's just 5. And over here, exactly, the probability of getting each result needs to be the same. Yep. And over here, that's 3 cubed and 6, so that's the same as 6 to the 4th, so that's 1296. So for instance, no, I would say, for example, the probability of check is not equal, well, it's equal to 1196 is not equal to 5/1296, which is equal to one of the other, this is check x. Okay, So I'll call this, 9b. Here's page 10. So what we were asked about was the probability of x equals 2. So let's try that. So the probability that x is equal to 2. So just looking at this table, I can just write down here 6 times 1 over 6 squared times 5, 6 squared. Now I could maybe add this up, so I get 6 times 25 over 1296. So 6 times 6 quarters. Hopefully I did that correctly. All right, 6 times 1. Good, perfect. So when we write this, the probability of the random variable x being less than or equal to 2. So again, what that is saying is this is the probability of getting two or less 6s on 4 rolls. So that would be the probability of x equals 0 plus the probability of x equals 1 plus the probability that x equals 2. And so I could write out that as 5 6 to the 4th plus 4 1 6 times 5 6 cubed plus 6 times 1 6 squared times 5 6 squared. So 5 to the 4th, that's 625 over 1296. And then you get 5 cubed, which is 125, times 4. So that's 500 over 1296 plus you get 6 times 25, which is 150. So 625 plus 500 plus 150 gives you, I think, 1,275 over 296. Okay, and we need to finish this up a little quicker. Let's see, I have C. I have the probability that x is greater than 2. So what I can do, oh, it needs to be, So that's the probability of x equals 3 plus the probability of x equals 4. But you could do it this way. I'm going to, because of time restrictions, I'm going to take the complement and I do 1 minus the probability of x less than or equal to 2. So 1,296 minus 1,275 should give you 21. And similarly, if we wanted to do one less than x less than 4, that's the probability of x equals 2 plus the probability of x equals 3. And that's all the time that we have for today. We worked through quite a few examples. If you have any more questions, feel free to send me an email at my RMC address. We have a office hour tonight at 7. If you have questions, some of these questions were from the assignment that we posted from last week, so feel free to drop by and ask questions, where you can work through questions, work through other questions that you have. And I wish everyone good evening. Take care, everyone. Thank you.